Pan from Georgia Tech Institute of Technology. He'll speak on global regularity versus finite time blow-up for compressible Euler equations.
Thank you for the introduction. And thanks. I'd like to thank the organizers, particularly Hamano, Philippe, and Eduardo for invitation to be here. And so in the past 4 years, I have been coming to IMPA, and stay for and spend some of most exciting time in my life in Rio. So this is a very beautiful city. And today I'm going to talk about some kind of the entry level of the. I prepared the lecture to be to accessible for the every math major undergraduate students with the background of ordinary differential equations. Okay, so they are. And first of all, I'd like to thank the sponsors, for their support from the National Science Foundations, and the other one is basically Brazilian, CMPQ, and which was supported my my time in Rio in the past 4 years, and through Sciences Without Border programs, and so here are some of my collaborators. So many are. So there's Hong Chai from Georgia Tech, and so there's a joint student with Xiamen University, and Gen Chen is my postdoc at Hale postdoc at the Georgia Tech, and he's going to University of Kansas this fall. And Sengui Zhu was a joint one of my joint PhD student with Yachun Li from Shanghai Jiao Tong University, and he graduated last year. He's right now as postdoc at the Chinese University of Hong Kong, and this is a current PhD student from Fudan University, and so you'll see these names appears in the talk, and so this is basically a renewed, old problems I'm going to talk about. Okay, so first of all, so we are going to talk. So I'm going to talk about so here's a little bit about introduction about compressible Euler equations. So more than actually, it's about 256 years ago, or 59 years ago. So the Euler actually published his his famous Euler equations for the inviscid flow in 1757. And today, so I'm still talking about the 1D version. Okay. So of course, in the past of time, so there are a lot of beautiful results in 1 space dimension, 2 space dimension, and 3 dimension. Okay, but there's still a lot of things that is not very clear yet, even in 1 space dimension. For instance, like a couple days ago when Dene talked about this vacuum problems. Okay, so they are here. So I'm even trying to avoid that, even avoid the vacuum. So we still have a lot of problems. Okay, so they are. So I'm still talking about it. So because I'm going to set my problem away from vacuum, so I'm going to use the Lagrangian coordinates. Okay, so they are. And then I'm going to only talk about ideal gas. So everything is put into as simple as possible. Okay? So the system looks like this. Basically, so you have 3 equations. The first one is the conservation of mass. The second one is the conservation of momentum, and the last one is energy equation. So here, if I use rho denote the gas density, and then V is 1 over rho, so which is the specific volume. And the U is the velocity, and this one is so this fancy E, so it's representing this internal energy. So and this is the total energy. Right? So P is the pressure, and the theta is the specific entropy. And here I said so that I'm considering the prototropic ideal gas, so that this pressure takes this form. And here, so this theta is the specific entropy, and the reason why so usually, so in the many textbook, so that we use this S as the specific entropy, but here I would like to use this because in another setting of Riemann invariance, S was often served as one of the Riemann invariants. Okay, so this is why. Okay, here gamma, so the gamma, so it's called the adiabatic exponent, so most physical gases require gamma between 1 and 3. Okay. So they are, and here's the C sub V. Actually, this is the constant. So it's a positive constant, and they. Okay, so I'm going to consider the initial value problem. So the Cauchy problem assumes so that we are given this. So this is initial data of the specific volumes of velocity and the specific entropy, and so those are all also wonderful solution or wonderful functions like C1 functions or bounded, uniform bounded. I'll put the imposed condition later on, okay, to be more specific. So now let's see. So the compressible Euler equations serve as a very important example for the general hyperbolic conservation laws. And here I only talk about one space dimension. Actually, Daniel gave a very good so basically short introduction about the multi-dimensional version. So here let's put everything simple, okay, in one space dimension. And so to be hyperbolic, so the Jacobian matrix of this flux function has n real eigenvalues and n linearly independent eigenvectors. Okay, so if you want strictly hyperbolic, then you will require that all these real eigenvalues to be distinct. Okay, so this is and so basically under certain reasonable conditions on the initial data and on the systems, of course. So then the local well-posedness for the classical solutions, so basically it was symmetrizable or hyperbolic conservation laws is null. See, for example, like Friedrich, Godunov, and the Kettle, and the Deformos, and many others. And they are so they actually so the same thing actually was good in the multi-dimensional setting as so discussed by Denis. Okay, so we do not have much problem in the local existence of the classical solutions, in particular for most physical examples. Okay, so there are some things. For example, if a system is not symmetrizable, then what to do in a multi-dimension? That's a problem as well. Okay, even in linear setting. But okay, anyway, so there are as an analyst in PDE, so we often ask something, in particular for the evolutionary equations, right? For the evolutionary PDEs. So we often ask, so you have a local well-posedness, okay? What about the global behavior, right? So one of the very beginning, so from very beginning, so you ask yourself, so what the fundamental question is that, so how about the global regularities for your local solution? Or is there any finite time blow up? Okay. So so what was no? Okay. So there are actually so many textbooks actually has been putting this there. So basically, so what was no? There is like this. So for nonlinear hyperbolic conservation laws, no matter how small and smooth the data are, shock forms in finite time if initial data contains some truly nonlinear compression. So I try to use a little bit not that exactly description so that we do not get into the details of some definition of for like genuinely nonlinear and linear degenerate or so on. Okay, so for some terminology that if you just don't understand, just skip it. Okay. All right. So so this is a very beautiful statement, and but it's more or less leave a little impression to people that so. Does that mean so does that mean that so for large data this is also true? Okay. Or what do we do? Do we know? Actually, so from the scientific fact and from the language point of view, so there's nothing wrong with this statement, right? It just gives some impression. So but anyway, so let's see. So what not really know? So there is that. So if data is large. If your data is not, for example, like a small smooth perturbation near constant equilibrium, then many things actually are not known, not really known. Okay. So so for instance, so let's pick up there, for example, the most important example, that's a compressible Euler equation, and then let's see what know and what we know now and what we don't know. Okay. So this is the main purpose of today's thing, this lecture. So we want to know the conditions on possibly large initial data leading to global classical solutions or finite time shock formation for both isentropic and the adiabatic Euler equations. Okay, so this is this is what we mean. So I'll come back to the the definition of isentropic is means your specific entropy is a constant. Okay, so there's and the adiabatic is that's a non-isentropic case. So this is what do I mean? All right. So now see. So they are, as I said. So if you set everything in 1D and you ask this basic question. So they are one of the key technique is the very straightforward one is called the characteristic method. And then let's look at this simple characteristic method from like a scalar equation, the scalar case. And so we get familiar with that, then we see how it works on the systems, and then we keep going on. So consider so this is Burke's equation, and with so the initial data, so which is like a C1 by C1 is a uniformly bounded L infinity norm and the L infinity norm of the gradient. Okay, so they are. So we first define this so-called characteristic. So they are so they are generated by this velocity field. So by U, and then the directional derivative operator is defined as this, and then therefore you can convert this one. So this is Cauchy problem of PDE into actually infinitely many ODE problems. Okay, by infinitely many means that so actually for each initial point, then you have the systems of ODEs. Right. So they when the x naught went through the whole real line, so got infinitely many. So this is what it means. But also for each individual one, so this is very simple. Why it's very simple? Is because that so you read from here that around each characteristic line, so this is U is a constant. Okay, and then you use when it's constant, then you solve this characteristic. Then you find it's a straight line. Okay. And so then you can write down actually the explicit formula for the solution if you know the initial data. Okay, so this is given. So then you see for you have a global explicit solution like this, right? And it seems okay, solved the problem, right? But solving the Cauchy problem so means so you are not only solve for one point, you need to solve all the points and put them together. So then the question is whether you are able to put them together. So putting them together, that means also that's actually is a regulative problem, and then you're trying to see okay, so this so you choose W equal to the x derivative of U, and then you found the equation tends to take x derivative both sides. You found this. So this is actually is a Riccati type, and it's not hard either. So you can just find a solution, right? And once you wrote the solution formula, then you find something. So that you see this denominator. And then you can easily conclude that. So if the initial data has a non-negative slope, then you have a globally defined solution. And otherwise, so if at one point you have a negative slope, then then the solution blows up in finite time. And there are two remarks. First is that so this singularity is basically due to the shock formation, and so this is a little bit tricky, so need some argument to justify that. So let's just agree on that at this level. So okay. So and the second thing is that so this is large data theory because you didn't see any smallest condition on the initial data, right? So for this, and this can be generalized actually into for example, the case like when you have replaced this like here, the flux function is 1/2 of U squared by any strictly convex or concave f of U. Okay. So this is okay. So now let's see. So how do we generalize this into the for example system? So in 1964, actually Peter X, so they published a very actually short paper, and there are 3 or 4 pages, and so where he actually presented a very general theory, a general result on the general 2x2 systems. And okay, let's look at these 2x2 systems. And here's A, B, C, D are smooth functions of U and V. And so by Jacobian matrix, I mean the matrix A, B, C, D. Okay. So if this matrix has 2 distinct real eigenvalues, right? And so lambda is strictly less than mu for all the arguments of U and V. And then so if this is the left eigenvector for lambda, and this is the left eigenvector for mu, then you can see that. And then we assume the other thing. So usually, so for we know that if you have a vector, So vector field is not necessarily a gradient. Okay. So however, at least locally in the neighborhood of, for example, a point. So you are able to, so we all know this, right, from the ODE. So that I call the, in that context, it's called the exact equation. So you are able to find the integrating factor so that after multiply by integrating factor, so this will tend into a gradient field for certain scalar function R, okay? And similarly, so you can, so if you assume that there's a precise, integrating factor precise, so that this is another gradient. So this R and S was, so they're called by Lex, they are so-called Riemann invariants. And this was a generalization of Riemann's Riemann invariance introduced in 1860 for the gas dynamics. Okay, so we'll see that later. Anyway, so then after this, then you found that the 2x2 equations become this, and if you multiply first equation by phi, by second equation by psi, and this became actually so you got exactly so this two equations. So this resume what you have in the Burger's case, right? But here you only have two. You have two characteristics, two family of characteristics. Okay. So okay, now we know so around each characteristic, for example, backward the lambda characteristic. So you got the R, so like we call it x1, and around x2 corresponding to mu. So around x1 of t, so this R is constant. Around the x2 of t, S is constant. So then, okay, you got this very easily. So you see this L infinity estimate, right? So and the uniform, nothing was wrong so far. And okay, so now if you want to mimic what happened in the scalar case, so you are going to take the say for example, let's pick R, and then the case for S is similar. Okay, so if you do this, so you got this, right? The only thing that's a little bit of difference is that, so if you try to mimic this, you take x derivative both sides for this equation. So where you have, the lambda, so this lambda depends on both R and S. So therefore, so we are going to get a mixed term. And okay, so this can be done by notice this relation, and then you have this, right? Then trying to using an integrating factor using an integrating factor technique, so you are able to translate this into this. Okay, so you resume again, so the Riccati type, so the ODE, and then okay, so you are able to find this, right? And so therefore, if you want this to be blowing up in finite time, for example, so you need two cases. So first, you need this to be has a negative sign, right? And secondary, so you want this, so for example, for some finite time, this can for example, the absolute value of this part can approach into to 1, so that this denominator can vanish, right? So this is is it clear? So this is just a simple calculation, right? You see that? So this is two requirements, right? So now let's see what was done in this so in Peter Lack's this paper. So it's basically so he basically imposed the following two conditions. Okay, so the first, so if the initial data is a small near a constant equilibrium, right? And so that you are so there so the existence of the Riemann invariance require the existence of this integrating factors. So in general case, you will need smallness. Okay, so the first. The second is he assumed that if this has this difference, this two characteristic, this characteristic speed has a positive gap. Okay. So so this is a constant. Then okay, so then this conditions are good enough to ensure the finite time blow up. So why is that? It's because, so look at this. So so if everything is bounded, and then if lambda and mu has the absolute value of lambda and mu has a positive lower bound k, then this h is a very good function. Okay, so this term is bounded, no matter so e to positive h or e to negative h. Okay, so it's bounded, and so the lambda. So if the data initial data is a small perturbation, so the L infinity bound tells you it's still a small perturbation near the constant. So everything is bounded, and so if this sign is initially negative, then it's negative for all the time. Okay, and also, so for that condition, using that condition, then you see actually here, so it's bounded by a constant. Okay, so then if the integration from 0 to infinity, actually, so this actually is a linear order in T, and so you easily see, so it's precisely like the Berg's case, so you can have the finite time blow up, and on the other case, so if you want the global regularity, so if this sign is opposite, then you see that, right? Because then this will never vanish, right? So the denominator is actually greater than or equal to 1, so there's no problem. Okay. All right. So now let's see. So for this 2 by 2 cases, also you see this series is essentially a small data series. So basically, so there are two places that need their smallness. So the first one is the existence of an integrating factor for Riemann invariance. So where in general you need the smallness condition. And the second is the condition for the uniformly strictly hyperbolicity, right? Okay. So in his case, so the series for very general setting. So that's so then you cannot avoid this smallness. So it's very reasonable. Okay. And later on, so this theory actually was generalized by there are many people. So here I only list 3 of them. So the Frisch-Jung actually so they generalized the theory to the n by n. So the elliptic field is generally nonlinear. Okay, and type nu so further generalized Frisch-Jung's result to the case of including, so some class is generally nonlinear and some classes are linearly degenerate. And so this actually even further generalized weakened it's called the weakly linear degenerate and not weakly linear degenerate. Okay, anyway, so that's what it is. So in all this results, so the initial data is basically setting as the small smooth perturbation near constant state. Okay, some paper actually basically just started with completely supported small perturbation, smooth perturbation near constant state. Okay, and so what was known here is that if the initial data is sufficiently small or smooth perturbation near a constant state, then finite singularity, so finite time singularity formation. This was wrong. Okay, singularity occurs for gradient. Finite time singularity occur for gradient if initial data contains some compression in any truly nonlinear characteristic field. And what was known, so there's the other part of theory of for example, global regularity. So is that, so if all the fields are linearly degenerate, for example, in typing New's case, so you cannot have a mix of the genuine nonlinear field and linear degenerate. Then you have global classical solution. Okay. So unfortunately, in all other cases, so you don't have that case. Okay. So you basically have both, in particular for the non-isentropic case, you have 2 genuine nonlinear field and 1 linear degenerate field. Okay. So that's what I want to remind you. Okay. So now let's see. So one of the so if I restrict compressive Euler into the isentropic case, so where the superficial entropy is a constant, then okay, so then you have the system become a 2 by 2 system. So then we say, okay, people immediately realize that this is just a special cases of the Lax's 2 by 2 systems theory, right? And so now let's check. So what the observation that we made so far, and to check so what was known and what was not known. And okay. So first of all, so we introduce some so the C is basically so called the local sound speed, and this eta is a quantity defined like this way, and which will made up as the Riemann invariance later on. I'll let you know. And so clearly, so there's a relation between, so because now pressure is only the function of V, and so you have this transformation, right? So it's a very easy formula. So you can just this is just algebra, right? And adapt to Lax theory, so you define lambda as a negative C and mu as a positive C, and so you have 2 exactly opposite characteristic, okay? And then you find that so the Riemann invariance was well defined and it's globally defined. So there's no smallness condition need for the existence of Riemann invariance if you look at the P system or the isentropic Euler. Okay? So therefore, so one of the restriction on the smallness for 2x2 systems actually was removed. Okay, so we don't need that. Okay, so then we have this, right? So you also have this L infinity estimate. So because as in the last case, and so what I want you remind you is that L infinity estimate from Riemann invariance offer only upper bound of density. Okay, so this is a little bit. You can see this easily from that. So where's my? So look at this. So this is our Riemann invariant, right? So you can see that this offers the L infinity bound for eta of v. Okay, eta of v is v to negative gamma minus 1 over 2, right? So gamma is bigger than 1. So this is negative power. So the v is 1 over rho. So you see, so L infinity bound of this guy is exactly so offers upper bound of density. It didn't say anything about the lower bound of density. Okay, and then this is actually was one of the mistakes made in several textbooks, where who claims that so that if there's a compression in the initial data, then without the smallest condition for the smallest condition on the initial data, then they claim that there's a finite time blow up. Okay. And there's proof as well, and but didn't carefully check this part. Okay. So okay. Anyway, so that's so most of what we know. So that's the only one thing that we're missing. So this is what I want to remind you. Okay. So now you do the similar thing like what in the last case in the general 2x2 cases. You just follow exactly the same scheme. Then you found actually. So this is the derivative quantity of the Q corresponding to R. So x derivative of R. And this is the quantity corresponding to the x derivative of the S. Then you found actually this quantity actually satisfies a Riccati type equation, and this A has explicit formula like this. Here's so this K sub C or K sub A are all their constants. Only depends on gamma, so it's positive constants. Okay. So now we look at this. Okay, look at this quantity. So this you basically have this 3 minus gamma over 2 times gamma minus 1. So the denominator is positive all the time because gamma is bigger than 1. Okay, and over here, so the 3 minus gamma is positive when gamma less than 3. Okay, it's negative when gamma is bigger than or bigger than 3, equal to 0 when gamma equals 3. Right? Okay, so it's very easy. So I want you to keep this in mind. And so now let's see. So from that theory, so for P system. So P system does not need the smallest condition on Riemann invariance, but for the other one, that is so the gap between the two characteristic speed is 2 times the sound speed, and which vanish at the vacuum. So if density can go to 0 or equivalently, so the specific volume can go to infinity, then the gap between two characteristic speed actually tends to 0. Okay. So this is something that you need to pay attention. So, however, so using this, so this is a good choice of Q and Y. So you can still see that that theory goes through without smallness if you have this, right? Right. Although that for example that coefficient A can vanish, right? But as long as this integral can go to infinity, right? So then the negative sign is there. So you still have no matter how large the data initial data are, so then you still can, for example, at the finite time, you can reach that 0 at the denominator, so you still conclude the abrupt, right? But okay, so now obviously, so what the A is, so you know so that eta has an upper bound. If gamma is bigger than or equal to 3, so then this is uniform bounded from below. Okay. So therefore, so for gamma bigger than or equal to 3, so the next theory actually implies this large data theory for the finite time short formation. Okay. So here basically, so the condition is like, the initial data is C1, and so the C1 norm is bounded, and so this guy has a positive rho bound because it's always positive, and then so it's equivalent to the density. Initial density has upper bound, right? So then this is differential shock if there is a point either this equal less than 0 and this or this less equal to 0. These two cases we call so. Either case, we are going to call this as compression. Okay, so this is the notion of compression. All right. So is there any question here? Okay. So now, so obviously, so look at this. So this could fail, right? So this one could fail if your density can go to 0. Okay. So now, for instance, so what about in several textbooks, right? So there's a proof of this. So where actually they are uniform positive lower bound of density was implicitly assumed. Okay. Now the question is, so is it true? Okay. So we know that if gamma is bigger than equal to 3, so there's no problem. So there's no that issue. So when gamma between 1 and 3, this is most physical cases are. Okay. So in principle, so that if this won't happen, if the density will never go to 0, right? Or approaching to 0, so then there's no problem, right? Or if we can prove that the density has a uniformly positive lower bound from below, then there's no problem for all the those proofs in those textbooks, right? Okay, so now what was so in reality? So in reality is that so actually so they are so an example studied by Riemann so implicitly imply that so they are so although the initial if you give an initial data that has a uniform positive lower bound for the density initially, but you still have actually the density can decay about 1 over t. So they are so 1 over t. So this is at the rate of 1 over t. So when t goes to infinity for Lipschitz continuous solution. And what Riemann actually studied is this this question actually. What Riemann studied is this actually in the case of this. He basically studied that so there's an interaction of 2 reflection wave. Okay, so it's a symmetric reflection wave. And if you started this center, so they are from the negative time, so then this is actually Lipschitz continuous solution. Okay, and so he actually started up to this interaction point, and so one can find actually in a book of Crown of Friedrich actually that that's some study of the explicit formula for the solution, and which was the density was expressed in the Legendre polynomials. Okay, and then where you can conclude exactly 1 over t for the lower bound of the order of the density lower bound. Okay. So therefore, so they hope to have a uniform positive lower bound for the density. In this case, actually, it's not possible in general. Okay. So okay now, so this was what was missing. Okay. So they fortunately, so 50 years later, after Peter Lax, so we are able to so find a remedy for this, and this actually can be done by a very so very easy to understand. The proof is actually just 1 page. Okay, so they are so in this paper, so this joint paper, so actually we are able to show that so that's the theorem in those textbook actually is correct. So that's very good. So the theorem is correct. You just need to add a little bit in the proof. Okay. So what this can be done is like this. Okay, again, so this is basically so this is for assuming gamma is bigger than 1, and this is a standard initial. So for the initial data, then so the P system, so the initial Cauchy problem for P system, so there has a global sigma solution if and only if there's no compression, and so that means so if there's a point there's a compression, then you have a finite time shock formation. Okay. All right. So now let's see. So the proof actually is made up by the following things. First of all, we notice that because for Riccardi, we can use the so this is like so this along the characteristic, this guy actually satisfies negative AQ squared, right? So it's decreasing, so it's will not so the upper bound will never increasing from the initial data. The upper bound. So it's one side estimate. Okay. Then you have a similar one side estimate of this of the other component. Okay. So this is what we have. Then okay, now let's see first. So if this condition, so if this condition, oh, so too quick, too much, does not respond. If this condition, this. If this condition actually give you a global Sequence solution, let's see. So there, first you have local existence, right? And second, so you have your L infinity bound by Riemann invariance. And then this quantity, so if this is positive by the Riccardi equation, you see it's never negative. Okay. So then we already have an upper bound, so then you have a lower bound as well. So it's uniform bounded. Okay, this is not yet enough to give the, for example, the C1 solution for the, for example, the Lipschitz estimate for the velocity and for density. Okay. The reason is because the Q has a weight, right? Okay, so now you need some for any finite time. If for any finite time, the density will never vanish. Then you are okay. So actually, so that for this specific kind of initial data, then actually in 1987, so there are Ronghua actually offered a proof, okay, by the polygonal schemes, and you'll see later on another proof, okay, a more elementary proof. I'll show you later, okay. So without using anything of this, just use the ODE comparison principle and the simple calculation. Okay, so then you see, okay, you have the L infinity estimate for this gradient. So then you have the global Sequence solution. Okay, so this is for the global regularity part. Okay, if there's no compression, then you have global Sequence solution. Now, okay, how about the shock formation? For shock formation, then okay, so we know that. So assume there's a point so that this guy there's a compression at the x bar. Okay, the other case is similar. And for gamma, if gamma is bigger than equal to 3, so this case you don't have to do, because Lux already know that. Okay, so we just said, so let's just focus between the gamma between 1 and 3. And so we just needed to, how do you find the density lower bound? Is basically you're trying to find you're trying to use what you know so far to, what we know so far is the one side of the estimate for the gradient, right? And the one side estimate of gradient can be settled from here. So we just write down. So this is from the Riemann invariance equation. So the t derivative of s equal to negative. So the sum speed times the x derivative of s. And we note that this is upon to a multiplication of a certain power of eta is just y variable. And y has an upper bound, but this is negative side, so we have a lower bound, right? Okay, for this guy, this is a similar technique, but this is positive side, so you have an upper bound, right? Now, fortunately, so the t derivative of eta is 1/2 of the t derivative of the difference between s and r, and then okay, subtract divided by t, or multiply by half, then you see exactly you have a lower bound, right? Okay, so you see here, so this k sub c is constant, y and the q are constant, okay, and this is exactly just an ODE inequality. And when gamma is between 1 and 3, you have this, then you can integrate. Okay. If you, upon integration, you got this A, okay, is exactly this form. Okay. This is a simple, this is very simple calculation. And then you find, okay, this A is 1 over t power. The integral in time is precisely log. Okay, when t goes to infinity is infinity. Okay, so therefore, so you have a finite shock formation. Okay, so so we know that this is not sharp. Okay, this is not sharp. So at the end I'll tell you what the sharp estimate is. Sharp estimate actually is 1 over t. So it's order 1 over t, and this can be done actually by for the general initial data with so it's purely refractive plus also refractive and compressive all the time. So this can be done, but I'll tell it later. Okay, so this is basically what. So therefore we had so we found that it's a very complete and accurate picture. So for the isentropic flow. Okay. All right. So so how about the four-wheeler? Okay. For four-wheeler, so first I'm going to show. So I'm going to show you that a lot of things is not known. So okay, so now let's look at the non-isentropic case. So that the specific entropy is not constant, and so then you follow the similar. So there are a lot of people also put a lot of time in the past several decades, and So there are a lot of wisdom over there. So it's exactly mimic what you did in the isentropic case. So then you found all these useful quantities, and then you have exactly similar things. Okay, so look at this. So this for the entropy wave. So this is essentially so they're like if it's a C1 solution, if you have, as long as you have C1 solution, so this is time invariant. So it does not depend on time, and so therefore, so you can essentially you just look at the 2x2 system, but with the then you have this flux explicitly depends on the x. Okay. Or it's non-autonomous. Okay. So then you follow it. So this you still call this lambda equal to negative c mu is a positive c, and then you still define this directional derivative. But then so these two guys, so the R and S define in a similar way, but they are not invariant, although it's globally defined. So because it changes. So therefore, the uniform L infinity estimate actually is not trivial, so not as trivial as the isentropic case. Okay. So look at the if you have isentropic case, then x derivative of m is 0. So then you don't have right hand side. So then you have a trivial L infinity estimate. Okay. However, so under certain condition, you'll see later, so that you still can have a uniform L infinity estimate. Okay. So now they're corresponding. So they are derivative variable is looking like this, a little bit more complicated. Okay. But it's no. And what the difference is that so that now you do not have the Riccati type equation. Instead, it's more or less like logistic, but it's worse than logistic. I'll explain later. In a logistic model, so this A and B has a definite sign, and here this B has a definite sign, but A is not quite that. So I explain. So this is where that's caused a lot of trouble, and a lot of that's why there are a lot of places is not known yet. Okay. So so now let's set down our definition, our conditions. So like in the isentropic case, so for initial data, we basically assume that it's C1 bounded, and so the entropy function actually is C2 bounded, and so then these are just some bounds. Okay. And the reason why this is positive is because it's e2 exponential function to the to something multiplied to the specific entropy. Okay. All right. So this is the condition to have the uniform L infinity bound. Okay. If you assume that the initial entropy has a bounded total variation, okay, then actually this is in this paper actually this Gang Chen, Robin Yang, and Qin Zhang. Okay. Prove that under the condition, so you have a uniform L infinity bound, so therefore you have this bound. Okay. It's a little bit complicated, but anyway, so you just need to remember. So keep in mind, so this is you have a uniform estimate of L infinity bound, and so again, so you have a L infinity bound for U, but not only upper bound for eta. Okay. So so now let's choose this guy. So the M3 is the say for the best upper bound of this quantity, and then you define this capital N. So this capital N in this way, what was that? Is essentially is the upper bound of this absolute value of A over B. Okay. So A over B is basically so these two things appear in this like a logistic type of ODEs for the derivative variable. Okay. So we know that. So this is this guy will serve as so will be very important, right? Okay. So now, so the one may ask. So the question is: so can we expect similar result like the isentropic case? So so does the initial compression lead to final time blow up? Right? It's very natural to ask that, right? So let's look at the example. So here you see an example that let's choose the basically initial velocity equal to 0, and then you choose your entropy function and the specific volume satisfy this. Then you found actually for any given non-constant smooth function theta 0 x, then you find a smooth function for v of x, and this is a stationary solution. Okay, it's a stationary solution. Of course, then it's a global smooth solution, right? Okay, so now let's check whether this guy can compress, can be compressive. So if you compute this y and the q, then you see this actually for this particular stringent solution, you have opposite sign. So then, as long as this is not constant, so it's never 0, right? So as long as it's not 0, so then this is the opposite side. So at least for one family, it's compressive. Okay, so this example shows that weak compression does not necessarily develop shock in finite time, right? When gas is not isentropic. Okay. So now what can we do? Okay, so you'll see that. So again, so you can do the similar thing like an isentropic case. So you obtain the one side of the estimate for this quantity, and using a similar technique that I used in the isentropic case, that similar calculation can be generalized to the non-isentropic. Then you find the exact same estimate like this. Okay, so you have time-dependent lower bound for density. Okay, and so we have a theorem. So the theorem is like this: under these two conditions, then this guy blows up in finite time if you have this relatively at one point, if the compression is stronger than this measurement, then you have finite time blow up. Okay. So this theorem assures that if initial compression is stronger than a critical value of this guy at that point, then shock must form in finite time. Okay. So keep in mind, I didn't talk about the existence of classical solution yet. Okay. All right. So now, so there are some. Okay. This can be generalized. For example, this total variation of the entropy for this type of theorem, it can be improved by imposed like locally. Okay. It's like if you send this guy like this guy go to 0, like this become approaching to constant, then it's consistent with classical theory. And okay, now I want to comment that this capital N actually is optimal. Why is it optimal? Because it can be reached by the stationary solution that I just constructed. Okay, this is a basic. You will see. So when this is equal to this, when this A is positive, then it's equivalent at one point. It's equivalent to this, and therefore this is equivalent to this. Right? Look at this. So this is the x derivative of this function, and those are just constant. So that means so x star is actually the local maximum of this quantity, right? So therefore so this is optimal, right? Make sense? All right. So now how about global regularity? So the question is, so do we expect similar global regularity just like isentropic case? Do purely reflective initial data lead to global regularity, like isentropic case? So this was not known because there's what was known is that for all the characteristic fields are linearly degenerate. So then typing news result offer this global regularity for small data. And then here, so even for small data, genetic small data for the Cauchy problem, so we don't know. So there's no such a theorem exist in the literature. Okay. So what was the negative? So I'm going to show a negative news. Okay. The negative news is that look at the example, very simple example. Let's choose our entropy like a tangent. Okay. And then I impose my eta is let m is the similar like the m. So in this particular choice, and then velocity like this. Okay. So I'm going to choose this eta later on, and then you can check this H3 and H4, so these two conditions satisfied. Okay. And the Dirac calculation shows that this is what you have. This is all positive, right, for any time. So this is even subjectively reflective for all the initial data. Now, okay, so you can check that. So this satisfies this. However, so because it's explicit, so you can look. So the evolution along, for example, this. Okay, this is forward. And for the side, so when x is bigger than 1, okay? So you have, this is an estimate about the press, so this so characteristic, and then this y satisfies this, okay? Now by this choice, what we can choose, what we see is that B is positive, like as I explained, okay? And it has estimate on B, because B only depends on the density lower bound, okay? And so this A, okay, this A essentially, so then you have this, right? this A essentially has the same sign as this G, okay? This G, by this particular choice, is actually negative. So now, think about that. If this A is negative, then this is worse than the Riccati, right? So if for certain, even you start with a positive initial data, in some finite time, this loss in this part can drive this below the 0, then you got a blow up, right? So this is the mechanism, right? Is the mechanism clear to everybody? Okay. So you can so this is what the calculation is. So A has the same size as G, okay? So using this, then you see this, right? And then you choose epsilon like this. Then you found that this is then you have finite blow up, right? So this example shows that the strictly purely reflective initial data is not enough to guarantee a global smooth solution, even for small data. Okay. So then this example can be generalized into for example, a theorem, right? For example, so you can just you can define a class similar to that picture. So this is a little bit complicated. So let me just like one is the Q condition, one is the Y condition. So the phenomenon is very clear, right? So if a gamma is between 1 and 3, so this is joint work with Izu. We just did 1 month ago. And under this assumption, so if this initial satisfies either this one or that one, so then the solution must blow up in finite time. Okay. Now, so the question is that, so we saw from that previous example that, so if this the negative part of A is extremely harmful to the global regularity. Now one may ask, how about we assume it's positive or non-negative? Okay, if you are able to assume this is non-negative everywhere, this is equivalent to this. This is okay. This only depends on the initial entropy. Okay, so it's okay mathematically. Okay, so then if that's the case, then one conclude that Y and Q because then it's better than the Riccati. So then you have also lower bound. Okay, if you ask, for example, initially it's non-negative. So then, okay, you have upper bound and lower bound. So so it's beautiful. Then you have a beautiful result of a global regularity, right? So this is a beautiful dream, right? Let's check the reality. So the reality check is that this guy, if ask this is non-negative for OX, is equivalent to this. And so think about, so then this is a concave function, right? Over the whole line. And this contradicts to the reality that M is uniformly bounded, unless the gas is isentropic, so that this is equal to 0. Okay. Right. So basically, for the entropy, this guy can, so for example, the M can go to so S entropy, so specific entropy can go to negative infinity. That's where you ask. It's basically so that you require that the flow can reach that absolute 0 of temperature. And for flow, this is not possible for our flow. So for some solid crystal, it's possible. Okay. So now, so the question is, how about the strong reflection initial data? So this is impossible because Y and Q tend to 0 at the far field. And how about the fast decay of A? Okay, let's see. It's maybe. So here's a toy model. It's basically, so if you have this, so you have negative side, but it's a fast decay, right? Then if Z0 is less than 1/2, then it's impossible. If Z0 is bigger than or equal to 1, then you can prove this is global exists and has a uniform bounded. However, you cannot ask that, for example, our Y or Q always bigger than or equal to 1, right? As I explained, right? So then, therefore, it will become very dedicated to assume to find a relatively simple set of physical conditions for global regularity. Okay. So now, so they are, but if you look at if you impose some bounding condition, then it's possible to ask A is always non-negative, right? And physical. So then this is possible. Okay. So now here's some reference, and this is so in this set of basically in this work as also mentioned earlier by the Dene. So this proof of local existence and finite time singularity of formation due to vacuum, and see also this Shipman's paper for this is also work for multi-dimension. And the Thomas series actually in 1985 have a very beautiful result on the singularity formation for multi-dimensional cases and using the functional. Although we don't know what the singularity is in that paper, but this is very beautiful. And the data is set as a perturbation or compactly supported perturbation in near constant equilibrium away from vacuum. Okay. And for shock formation, this is for shock formation actually for the relativistic Euler and for classical Euler, compressible Euler. This is a big book. This is a relatively slightly thinner book, okay, more than 500 pages. And so this is for the multidimensional shock formation for special classes of initial data, small. And so this for in these two papers actually also mentioned earlier by Dene. So Grayson and Sarah and Sarah also for multidimensional isentropic and non-isentropic. So there's a multidimensional global existence of classical solution, but there's a vacuum, and also there's basically the condition that for this dispersion, right? So it's basically actually does not, so it requires that velocity cannot be bounded at the far field. Okay. So that's what not consistent with our initial data. Okay, so this is basically for the optimal density lower bound. So this is for the isentropic, and this is for the both isentropic and non-isentropic. Okay, so I'll stop here, and so basically, we know something. We knew something before. We know a little bit more now, and there's still a lot of open problems, and we need your talent or help or support. Thank you.